The topic is graphs and networks in engineering. This is the part of the application in the that comes in advanced linear algebra fifth module. This is going to present one of the team, Pramod, Meghana, and Kavya. These three are 8th semester ISC students. Yeah, they given already these presentation in last year. They did very well. Therefore, again, I'm requesting these three persons. They're going to give a presentation for our sixth semester students. Uh, then you please be alert and listen what they're going to explain, and also they explain the problems. After that, we are giving a time to ask the questions once you complete the presentation. Yeah, welcome. And also, I welcome Dr. Gunavati, Associate Dean, and also those participants, those who are joined for this webinar. We heartily welcome you all for today webinar. Thank you. Over to Pramod. Hello.
Yes, ma'am. Yes, ma'am.
Yeah, Gunavati, please put a record, ma.
Yes, ma'am.
Meghana.
Yeah, please put a record. Okay.
Yeah, Pramod, can you share the screen? So, hello everybody. Today we'll be explaining about the engineering applications on linear algebra, that is graphs, networks, and other related topics. So, beginning with the introduction. So, where do we usually use linear algebra? We actually use it in chemistry, for example, wherein we check out row reduction process that is actually included in this PPT, wherein we use it to check whether the elements in a complex or a complicated reaction. And in physics, also in some areas, we make use of graphs and networks. So, and so throughout this PPT, we will be explaining about graphs and networks, and also about electrical networks, that is Kirchhoff's law, as an application to this topic. So what is graphs? Graphs is a collection of nodes which are joined by edges. So in that figure, you can actually see that there are four nodes, and so the connections between those nodes are known as edges. So you can see that there are five edges. And in the second diagram, you can see that we put an arrow on each edge to indicate the positive direction for currents running through the graph. So an application of these graphs and networks, we see that we use it in currents and voltages graphs. So that is Kirchhoff's law. Further ahead, we'll be explaining about that. So in the second figure that you can see, we can also see the incoming edges, outgoing edges, for each of those nodes, and the edges are also depicted in circles, that is 1 2 3 4 5. Next line. Incidence matrix. So the incident matrix of this directed graph has one column for each node of the graph and one row for each edge of the graph. So the columns are depicted by the nodes of the graph, and the rows are depicted by the edges of the graph. So when it's an incoming edge, we represent that in the matrix as +1. And when it's an outgoing edge, we represent it as -1. And if there's no edge like that, we represent it by 0. So according to the first in matrix that is there, if an edge runs from node A to node B, the row corresponding to that edge has -1 in column A and 1 in column B. So all the other entries in that row are 0, because there's no incoming edge or outgoing edge. So if we were 1001 studying a larger graph, we would get a larger matrix, but it would be sparse. Most of the entries in that matrix would be 0. So this is one of the ways that we can depict the graphs in terms of matrices. So in next is fundamental spaces of incident matrix. So suppose we have a matrix. So the order of that matrix we give it by m by n. So that matrix is an incident matrix. So m represents the edges and n represents the nodes of that graph. So there are four types of fundamental spaces, that is row space, column space, null space, and left null space. So row space is the combination of the row vectors of that matrix A. So we equate this as C of A to A transpose. So that is how it's depicted. So the column space of the transpose of A. What is column space? So column space is, it consists of all the columns of that matrix, given matrix A. Null space is similar to a homogeneous equation that you can see it as Ax is equal to 0. So all the solutions of that equation will be the null space. And another one is left null space. So we can depict the left null space as the null space of A transpose. So the transpose of matrix A, and for that the null space. If we do the null space for that A transpose, then we get the left null space. So row space. So a vector V in the row is in the row space of an incidence matrix if it is perpendicular to 1 1 1 1. So that is the vector 1 1 1 1. So we consider a graph here. So you can see that there are two loops and there are four nodes and there are five edges in this graph. So for this you need to write a incident matrix. So the given incident matrix, you can see it here. So for 1 to 1, you can see that it is -1. So -1 means it is an outgoing edge. And if it is +1, it's an incoming edge. If it is 0, there is no incoming or any outgoing edges for that particular node. So how do you find out the row space for this is that row 2 and row 4 were the sums of other rows in the matrix. So you can cross verify this. So row 2, you can see the first column. -1 plus 0 is what? -1 itself. So that is the sum of the other rows of the matrix. So this indicates linear dependence in the row space, and we can throw such rows away when finding a basis of column space of A transpose. But each row of A represents an edge. So what happens if we modify the graph by throwing these edges away? We get a minimal spanning tree. So minimal spanning tree means it's the smallest of the edges where it contains all the nodes and there are no loops. So each basis vector of the row space of the edge node incident matrix represents one of the edges in a minimal spanning tree for that graph. So this is the simplest and the smallest simplification that can be done for this network. So further ahead, you'll understand all this when we show the problem. So how you are supposed to solve the problems. Next is column space. So the column space, as I said, is the linear combination of all the columns. So each equation in the restrictions representation of the column space of the edge node incident matrix is equivalent to the independent small loop in that particular network. So how can we say that vector B is in the column space of an incident matrix? So let us consider AX, it is a vector of differences. So if we add differences around a closed loop in the graph, the cancellation will be 0. So when you all add a plus, minus and everything, obviously it will be 0, right? So if B is in the column space of A, then its components around any loop add up to 0. So by testing each of these loops, we can say that B is in the column space. So this is an example for column space. This is the same graph that was taken even for row space. So you can see there are four nodes, sorry, and five edges for that loop, for that network, and two loops are present. So correspondingly, you'll write the required incident matrix, wherein you'll consider incoming edges and outgoing edges. So here we can see that row 1 plus row 3 is equal to row 2. So row 1, that is -1 plus 0, that is -1. So that is equivalent to the second row itself. And another combination is that row 3 plus row 5 is equal to row 4. So if we consider it in the equation for Ax is equal to B, we can write similar equations, that is b1 plus b3 is equal to b2 and b3 plus b5 is equal to b4. So here we can read these off from the small loops in the graph. So after segregating into smaller loops, we get another diagram that's in the next page. So next is null space. This is the set of all the solutions for the homogeneous equation that I said earlier. Ax is equal to 0. So for that equation, all the solutions will be the all the set of all the solutions will be the null space for that particular matrix. So again, we are considering a graph here, and for that particular graph, we are writing the incident matrix with all the incoming edges as +1 and outgoing edges as -1. So the null space of this incident matrix is spanned by the vector 1, 1, 1, 1. So it goes on until how many ever uh, nodes are there in the graph. So if we view the graph as an electrical circuit, so this is the application that we are discussing here. We can view the input vector, that is x, as representing the potential at each node, that is a voltage, and the output of that vector will be the potential difference across the edges. So if all potential differences are zero, then we can actually say that the voltages are the same. So a null space of a matrix is a line in R power n. Its dimension is n minus r is equal to 1. So this can be given as a null space example. So every solution to 1100 for the equation xy is given to as 0. That is nothing but ax is equal to 0. So the matrix A is here 1100. So is in the form of minus y for some y. So the null space will be a spanning vector which will span across -1, 1. So you can actually see here the null space of 1100 is depicted in the graph below. So that line depicts the null space of the given matrix 1100. Last fundamental space is the left null space. So as I said, this is the set of all solutions to A transpose Y is equal to 0. So that is the null space of its transpose A, null space of a vector A with its transpose. So that equation is given there. So the word left in this context, it means that the fact is A transpose Y is equal to 0, that is equivalent to y transpose A is equal to 0, where y acts on A from the left. So each basis vector of the left null space of the edge node incidence matrix represents an independent small loop in the network. So I said, right, there are smaller loops in that network. Before diagram, we could see two loops. So the positive entries indicate positive flow, while the negative entries indicate backward flow. So this is an example. We have considered the same graph, and that for that corresponding graph, we have written a incident matrix with considering incoming and outgoing edges. So here you can see A transpose Y is equal to 0. That is the equation. So A transpose, we have written the matrix, and Y is the set of Y1, Y2, Y3, Y4, Y5, Y6, which is equal to 0. Now multiplying the first two matrices, we get these four equations. That is minus y1 minus y2 minus y4 is equal to 0. y1 minus y3 minus y5 is 0. y2 plus y3 minus y6 is 0. And y4 plus y5 plus y6 is 0. So what actually these equations means is that each represents the net flow into which is or 0 out of depending on the point of view a node. So for circuits, these are Kirchhoff's current law. We find that every loop current is a solution to the current law, and that all such solutions are built from sum of loop currents. So that is the basic idea behind these equations. So over to Kavya, she'll be explaining further ahead.
Yeah. So far we've discussed about the fundamental subspaces, which is left null space, row space, and the column space. So here in the slide, you can actually look into the Python code, which actually implements those fundamental subspaces. So here we use NumPy and SymPy libraries from Python, which have pre-built methods. We just need to call them in order to find the fundamental subspaces. So SymPy is a Python library for symbolic mathematical equations. So basically, so if you, for example, if you consider an equation, for example, if z is equals to x plus y plus x minus y, so it equates to 2x. So if you directly write it as a string, then that's not going to compute. So for using SymPy, you can actually compute that and return 2x. And NumPy is used for all this rank, null space, and all that. So here we are hard coding a matrix. So this is the matrix that we are using. And in order to find the null space, rank, left null space, column space, and row space, we just have to use the methods which are already present from the NumPy library. So a dot rank gives the rank of the matrix. So similarly for null space, a dot null space, left null space as since transpose. So a dot t represents the transpose dot null space. So this gives the left null space. Similarly for the column space and the row space. So row space is basically the transpose of A getting the column null column space. So this Python code fetches us the 4 fundamental subspaces. So next, coming to Euler's identity. So this is one of the basic identity in the graphs in the network, which is used in many applications. So Euler's identity is for every graph in a plane. So we can apply this Euler identity to all the graphs. So basically concerning the connected graphs. So we say connected graphs when each and every node has a connection to each and every other node. So that is connected graph. So Euler's identity is represented as the number of nodes minus number of edges plus the small loop. So within the graph, we might have loops or we might not. So loops are also considered. So when this equation sums to 1, so this is Euler's identity. So, so whenever a graph is a planar graph, so planar graph in the sense, so when we have edges and each and every edge is not intersecting with any of the other edge. There are no overlapping edges, so that are called as planar graphs. So all the planar graphs leads to 1. So the Euler's identity is applicable to all the planar graphs, basically. So this means the rank of a matrix, which is represented by R, is equals to n minus 1. The dimensions of the left null space is m minus r. So when we actually put these values into the equation, we get this n minus m plus m minus r. So r is substituted by n minus 1. So when we solve this, you get it as 1. So this is Euler's identity. Coming to the applications of fundamental subspaces. So here we're basically discussing about the Kirchhoff laws. So there are two main Kirchhoff laws. One is the Kirchhoff's voltage law and the other one is the Kirchhoff's current law. So here we're considering this network. So if you can see, there are 4 nodes and 5 edges. So incidence matrix is made up of the edges and the nodes. So the columns represent the nodes and the edges represents the rows. So since it's 4 node and 5 edges, so it is basically 5 cross 4 matrix. So wherever there is a outward edge, it is minus 1, and towards it is plus 1, and when there is no edge, it is 0. So basically, so if you can consider this first edge, it is flowing from 1 to 2. So for 1, it is outward edge, and for 2, it is an incoming edge. So for 1, it is represented as plus 1, and for 2, it is represented as, for 1, it is represented as minus 1, and for 2, it is represented as plus 1. And since this edge is between only 1 and 2, 3 and 4 doesn't have. So it is basically 0. So when you apply the same for all the other edges, you end up having this incidence matrix. So yeah. Okay, so coming to the Kirchhoff's voltage law. So it basically says that the components of AX equals to B adds to 0 around every loop. So this is AX, the matrix is adding up to 0. So AX basically represents the difference in voltage. So that is the voltage difference. So x1, x2 is considered to be as the currents flowing. So components xi of the vector x describes the electric potential at the nodes I of the graph. So this ax is a vector that describes the difference in potentials across each edge of the graph. So with this equation, we can actually solve this. So the potential difference is 0 on each edge if each node has some potential. So we can tell what the potential is by observing the electricity flow through the network. But if one of the node in the network is grounded, then that potential is 0, so that we can determine other potentials out of this. We can also say that creating a matrix C using Ohm's law and information about the conductance of edges, and use the matrix to determine the current Y I on each edge. So that is Kirchhoff's voltage law. So using this Kirchhoff's voltage law, by testing each and every loop, voltage law decides whether B is in the column space or no. Next, coming to Kirchhoff's current law. So the equation, yeah. So the equation basically says that A transpose multiplied with Y is equals to 0, which means flow in is equal to flow out at each and every node, which is nothing is lost, so nothing is gained. So whenever the current or forces are balanced, we get A transpose Y equals to 0. So that is the main statement of Kirchhoff's law. So here Y is a vector with the components Y1, Y2, Y3, Y4, Y5. So they are basically the current at each and every edge. So if you can remember that the previous network that we used, so there were 5 edges. So these Y1 through Y5 represents the current on each edge. So vectors in the null space of A transpose corresponds to the collection of currents that satisfies Kirchhoff's law. So here in the picture, you can see the potentials at each and every node are represented by the vector x. Since there are 4 nodes, we have x1 through x4. And E is the potential difference, which is AX, which we have already discussed. So x2 minus x1 is the potential difference. So from the node 1, from the node 2 to node 1, what is the potential difference current? So then we have Ohm's law, which is again discussed in the next slide. So we have Ohm's law, Y equals to CE. So C is nothing but the conductance, and E is the potential difference that we are obtaining here. So substituting with the currents on each and every edge, we get Y transpose Y, A transpose Y equals to 0, which defines the Kirchhoff's current law. So as an example, so while substituting the matrices to A transpose and Y, so this is how it looks. So we have this A transpose T, which is the transpose of the incidence matrix that we just saw, and Y as a vector of currents through the edges, which is equating to a zero column matrix. So multiplying the first row by the column vector Y, we get, since there are only 3 non-null values, so we get minus y1, minus y3, and minus y4, which is equated to 0. So this tells us the current flowing out of node 1 is 0. It is a balanced equation or conservation. Y1 and minus y2 equals to 0. So the current coming out into the node 2 is balanced, while the current going out. So similarly for the third row and the fourth row as well. So when you multiply this row with this column, so we get y2 plus y3 minus y5 equals to 0, and the final row y4 plus y5 equals to 0. So adding current sources changes the A transpose Y equals to 0 in Kirchhoff's current law to A transpose Y equals to F, because there are some sources added up. So the right hand side is no more 0. So combining the equations, so we have E equals to AX and Y equals to CE. So A transpose Y, here Y is substituted with CE. So we finally get this A transpose, and instead of Y, we have C into E, that is equals to F. So this is Kirchhoff's current law. Finally, coming to Ohm's law. So in the real networks, the current Y along an edge is the product of 2 numbers basically. So these 2 numbers are the potential difference and conductance. So coming to potential difference, we already know. So it's a difference between the voltages among 2 nodes, which is represented with AX. So it drives the flow. And the other one is conductance. So conductance measures how easily the flow gets through. For example, conductance will be different for different kind of objects. For metals, it is high, and for plastic, it is low, and for semiconductors, it's infinity, which means the current passes very easily through that kind of materials. So, so this Ohm's law can be equated as conductance times the voltage difference. That is C multiplied with the voltage difference AX. So we have this AX with a negative sign, if you can see. So this negative sign tells that AX is basically voltage difference. That is from one node to another node. Since here we are calculating it from the higher potential to lower potential, we are getting this negative sign. So usually it is calculated from lower to higher, from node 1 to node 2 if we say. But here the potential difference is x2 minus x1, not x1 minus x2. So this negative sign is added for this Ohm's law. So we can relate this Ohm's law with the Kirchhoff's current law. That is A transpose Y equals to 0. We have that equation for Kirchhoff's current law. And here in place of Y, if you substitute minus C Ax, we get A transpose C into X equating to 0. This must be a single equals, so it's a mistake here. So we can find this Ohm's law applied in many places. So each and every application has its own Ohm's law. So if you can take an example, we have this Hooke's law in springs. So basically, so it's a law of elasticity. It has an equation of F is equals to minus kx, which says that the force applied is equal to the elasticity and the change in the length. So if you can relate that to Ohm's law, so elasticity is the conductance here, and multiplied with stretching. So we have the voltage difference, and whereas with the Hooke's law, we have this stretching. So this is how Ohm's law can be applied to any other application. So this is a simple example of Ohm's law. I mean, an application. So since we've discussed about this fundamental subspaces, we should also know where this is actually used. So it is easy to highlight the need of linear algebra for physics. So this is all basically physics, the Kirchhoff's current law, voltage law, all those. Quantum mechanics, like as I say, Hooke's law, is entirely based on it. Also important for time domain control theory and stresses in materials using tensors. So in circuit theory, matrices are used to solve for current or voltage. So in electromagnetic field theory, which is fundamental course for communication engineering, conception of divergence, curl are important. For other fields such as engineering, computer memory, extensively uses the conception of partition of matrices. So if the matrices size gets larger, then the space of the computer memory, it divides the matrices into submatrices and does the calculation. So for all this, we can also implement it and get the results. So instead of manually calculating everything. So as like we did for fundamental subspaces where we had a Python code to calculate all. So we can also try computing or writing the code for all this to get the computations. So this is the uses of fundamental subspaces in engineering fields. So over to Pramod, he'll be teaching the problems going forward.
So we have learned the theory part, what are the subspaces, how to construct an incidence matrix and uses. Now let us solve few problems based on these topics. First, how to find the null space of the given network. So if the network is given, first we have to write the incidence matrix for the network. Then later we have to write Ax is equal to 0. That is the equation to find the null space. It's already taught. So by finding this equation, we will get the null space n. If a vector R is given, and we have to check whether that whether it is present in the row space, then the null space, we have to check whether the null space and this vector R is perpendicular to each other or not. So if it is perpendicular, that is n into R, it should be equal to 0. Then it belongs to the row space. If it is not equal to 0, it does not belong to row space. So these are the things which you have to do. Next, how to find the current voltage if a network conductance and F is given. F will be given, conductance is given. If we have to find the current and voltage of the network. So first for that, for the given network, first what we'll write, we'll find the incidence matrix, then find the transpose of the matrix, then write the conductance matrix for the conductance given. Then A transpose CA is equal to A1. This is already taught in the Kirchhoff's laws. So then we will equate A1x is equal to F. So some potentials will get added, some sources, so it will be equal to F. So then voltage is V is equal to I into R. So I is nothing but the conductance is minus C will substitute, and V will write it, it is nothing but AX. So AX, that is a null space. So minus C AX, which is will be equal to voltage. So from this we'll get the X and Y values. So Euler's formula also we learned. Nodes minus edges plus loops is equal to 1. So based on this two examples, I'll tell a connected graph with 7 nodes and 7 edges has how many loops? So number of nodes, how much they have given? They have given it as 7. Edges, how much they have given? 7. So 7 minus 7 plus loops we have to find is equal to 1. So 7 minus 7 is 0. So loops will be equal to 1. So there is one loop in this connected graph. Next question we'll see. A tree connecting 6 nodes has dash edges. How to find this? So tree means we know that tree will not contain any loops. So there will be 0 loops. So the number of loops in this will be 0. So the nodes they have given, we have to find the edges. So 6 minus edges plus 0 is equal to 1. So if we shift the edges to this side and 6 minus 1, it will be 5. So the number of edges will be 5. So using the Euler's formula, we can find the, if any two data is given, we can easily find the other one. So if nodes are given, nodes, edges are given, loops can be found out. Edges and loops are given, nodes can be found out. So similarly, the loops also can be found out. So now we will solve few problems. So we'll solve few problems, some model paper problems. So this problem was is in one model paper 1. We can see for the following graph, write down the 5 cross 4 incidence matrix A with 2 loops. Find one solution to AX is equal to 0. That is the null space. Two solutions A transpose were left null space, and we have to reduce the matrix A, that is the incidence matrix, to echelon form. So this problem we'll solve now. So the question is written here. So the graph is given. So it has 4 nodes and 5 edges. So first we will write the, we'll find out the incidence matrix. So incidence matrix A is equal to, so the how many nodes are there? 1, 2, 3, 4. So the number of edges, how many are there? 1, 2, 3, 4, and 5. So first edge, we'll take the first edge. So you can see the first edge here. For the edge 1, 2 nodes are connected here. So for the node 2, it is an incoming edge. For node 1, it is an outgoing edge. So for outgoing, what we have to put? We have to put it as -1. For our incoming edge, what we have to put? +1. For 3 and 4, the node edge 1 is not connected. So for that, we will put it as 0 and 0. Next, edge 2 will consider. Edge 2 is there. In edge 2, which are the nodes connected? 1 and 3. So for 3, it is an incoming edge. For 1, it is an outgoing edge. So for 1, it is an outgoing. So it will write it as -1. For 2, there is no edge. So it will be writing it as 0. For 3, it's an incoming edge. We'll write it as +1. Then we'll write it as again 0. Next, for 3, the edge 3. 2 and 3 are connected. For 3, it is an again incoming edge. For 2, it is an outgoing edge. So we'll write it as 0, -1, 1, and 0. Then for the edge 4, when we consider the edge 4, 2 and 4 are connected. For 4, it is an incoming edge. For 2, it is an outgoing edge. So we'll write 0, -1, 0, +1. For the fifth edge, 3 and 4 are connected. For 3, it is an outgoing edge. For 4, it is an incoming edge. So we'll write 0, 0, minus 1, 1. So this is the incidence matrix. So first part of the question they have given us, write down the 5 cross 4 incidence matrix A with 2 loops. The 2 loops are given, for that the incidence matrix is found out. So this is the first part of question. Next they have given, find one solution to Ax is equal to 0. That is, we have to find Ax is equal to 0. That is the null space. So A is already given here. Already we have found out. So it's minus 1, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 1, 0, 0, minus 1, 0, 1, 0, 0, minus 1, 1. So let the the vectors x be, we can write it as x1, x2, x3, x4. Because 4 nodes are there, we have to find 4 potentials transpose. So we'll write x1, x2, x3, x4. We'll equate it to 0. 0. So now we'll solve this matrix. So we'll get, so for the first row, minus x1 plus x2. So that will write it as x2 minus x1. Again, for the second row, minus x1, it is 0 here, then plus x3. So that will write it as x3 minus x1. Next, for the third row, minus x2 plus x3. So that is x3 minus x2. For the fourth one, again we have x4 minus x2 plus x4. That is x4 minus x2. For the fifth row, again we have minus x3 plus x4. So it is x4 minus x3. So this will be equal to 0. So if we equate to 0, so you'll get it as x2 minus x1 is equal to 0. x3 minus x1 is equal to 0. x3 minus x2 is equal to 0. Again, x4 minus x2 is equal to 0. x4 minus x3 equal to 0. So if we solve, we'll get x2 is equal to x1. Here x3 is equal to x1. Then x3 equal to x2. Then x4 equal to x2. Then here x4 equal to x3. So we can see that all are equal to one another. So from this, what we'll get, x1 equal to x2 equal to x3 equal to x4. So which is, so x1, they have told it is always spanned by the vector 1, isn't it? So we can we'll get the answer. We'll get the matrix X as, so the potentials as constant A into 1, 1, 1, 1. So this is the potentials. So it will be A. So you can take A common outside, and this will be the potentials. So this is the one solution for the for equation Ax is equal to 0. So this is how we solve. So first we have tried Ax is equal to 0. We have whatever the matrix we have found out, the incidence matrix that we write down. Then we write the, we assume the potentials. Then we multiply, we solve the equations. So as I told, the matrix will be spanned by the vector 1. So we can consider any of the constants as A. A can take A outside, 1, 1, 1, 1. So A1 is the value of the potentials or the nodes. So this is how we solve the matrix. Next, we'll solve two solutions to A transpose Y is equal to 0.
Hello? Hello, Pramod? Hello? Hello, Pramod?
Hello?
Yeah, your voice is not audible, I think so. Please.
Oh, yes, ma'am. 1 minute. One minute. And share the screen. Next, we'll continue with the problem. Now we have to find the solution. A transpose y is equal to 0. For this, we have to find two solutions. So A is already given. The transpose of that matrix we'll write down. -1, -1, 0, 0, 0. Again 1, 0, -1, -1, 0, 0, 1, 1, 0, -1. Again 0, 0, 0, 1, 1. So this is the transpose, and we'll assume the y values. Since 5 nodes are there, 5 nodes. Since 5 edges are there, we will assume 5 values. y1 is y1, y2, y3, y4, y5. So we will write it down here. y1, y2, y3, y4, y5 equal to 0. Now we will solve the equations. So for the first row, again it is -y1 is -y2 is equal -y2 is equal to 0. For the second row, it will be y1. Again, we can see minus y3 minus y4 is equal to 0. Again, for the third row, y2 plus y3 plus, sorry, minus y5 minus y5 equal to 0. Again, for the third row, it is y4 plus y5. y4 plus y5 equal to 0. So these are the things while solving this we get. Now these 4 equations we have to solve and get the values. So we'll consider these 4 equations. So minus y1 minus y2 is equal to 0. So first what we'll write, minus y1 is equal to minus y2. So we'll shift the y1 to that side. This is one equation. Second equation we can write it as, so we got y1 is equal to minus y2. So instead of writing y1, we'll write it as minus y2. So minus y2 minus y3 minus y4 is equal to 0. Next, third equation, y2 plus y3 minus y5 is equal to 0. Before writing that, we'll write y4 plus y5 is equal to 0 they are given. So y4 is equal to minus y5. So this in the third equation we can substitute. Instead of writing minus y5, we can write it as what? Minus y5 Instead of that, we can write minus y4. So we'll get it as y2 plus y3. Y2 can also be substituted. So we'll get it as y2 plus y3. Instead of minus y5, we'll write plus y4 is equal to 0. So we can see this and this equation are same. So if we cancel this minus signs, both equation will be same. So we'll get finally 3 equations. This is equation 1, equation 2, and equation 3. So finally 3 equations we'll get. So we'll assume few values. First, they are told to find 2 solutions. So for the first time, we will assume y2 as 0, y2 as 1, and y3 as 1. So substitute in these equations. So y2 as 1 again. So in the equation 1, y1 will be equal to minus 1. Again, we can substitute in the say equations. Y2 as 1, y2 as 1 we have taken. So 1 plus y3 as 1 plus y4 is equal to 0. So we'll get y4 is equal to minus 2. Now, if we know y4, y5 is easy to find. So what is y5? Negative of this y4, it will be 2. That's it. So this is one solution. So y will be equal to, what is y1? y1 is minus 1. Again, y2 is 1. y3 is 1. y4 is minus 2. y5 is 2. So this is one solution. To find one more solution, they are told to find 2 solutions. Now for the second time, we'll assume remaining 2 values as y3 as 1 and y4 as 1. So if we substitute the values, we will get the answer.
One small clarification with Pramod.
Yes, ma'am.
Yeah, how to choose the values? You please explain. Is that take randomly?
Zero. We can, since the vectors for the ax we have taken as 1. It spans, the vector spans as 1. We can take it as 1. In some cases, we can take also 0.
No, my question is you are choosing y1 and first you choose some y2 and y3 are 1 like that, right?
Yes, ma'am.
And secondly, you choose.
We can also choose 0 and 2. Since they've asked to find 2 solutions, so
Yeah.
we are taking all possible combinations and we are choosing one.
Yeah. It's not necessary to take y2, y3 or if you want to take y2, y4 also and then y3, y5 also, right?
Yes, ma'am.
Yeah, they have to take any 2 combinations.
Yes.
They have plenty number of solutions, but I have to find 2 solutions. That's why I'm choosing this way. But not necessary to take y2, y3 and then y3, y4, y5 like that, right? They
Yes,
maybe go for other combination also, right?
Yes, ma'am. So
Okay,
somehow they have to find 2 solutions. That's all.
Yeah, and then different person get different set of 2 solutions, right?
Yes, ma'am. The solutions may not be unique here. The whatever.
Yeah. Please note that point. Please inform that point. The solution is not unique.
So here I have chosen y3 and y4 as 4. Again, if you substitute these 2 values in this, 1 plus 1 plus y2 is equal to 0, you'll get y2 as minus 2. So you get y2 as minus 2. y1 is nothing but negative of minus 2. So y1 will be equal to 2. Then y4 will be equal to, y5 will be equal to negative of the minus 1. So one more solution, what we get it as, y is equal to, what is y1? y1 is 2 y2 is -2, y3 is 1, y4 is 1, and y5 is -1. So this is one more solution. So they're told to find out two solutions. We have found out two solutions for the given equation. So this is the second part of the question. So first we wrote down 5 cross 4 incidence matrix. Second, we found out null space, that is Ax is equal to 0. Then two solutions, A transpose Y is equal to 0 also we found out. So this is nothing but left null space. Whatever we found out now, this is nothing but called left null space. So this any values we can choose, the solutions will not be unique. Any two combinations we have to choose and choose. If they ask only one solution to find out, only one time you can assume and solve the problem. Next, third part of the question is you have to reduce the matrix A to echelon form. So we will now reduce the matrix to echelon form. So this A matrix is given. First we'll apply one transformation. R2 minus R1 we can apply. So if we apply, we get -1, 1, 0, 0, 0, -1, 1, 0. Rest all the rows same. 0, -1, 1, 0, 0, -1, 0, 1, 0, 0, -1, 1. Next, again, we will apply two transformation. R4 gives R4 minus R2. Then R3 minus R2. So we'll finally, again, we'll get the matrix as -1, 1, 0, 0, 0, -1, 1, 0. Again, now R3 will change. The R3 row will become 0. Now, again, R4 will become 0. And we can see here it will be 0. Again, here it is -1. Again, it is 1. Next. Again, if we apply the transformation, R5 minus R4 -1, 1, 0, 0, 0, -1, 1, 0. This will be third row is already 0, 0, 0, -1, 0. The final row will become again 0. Now we will shift this 0th row will shift it. That's it. R4 to R3. I think everybody knows this to find echelon form. -1, 0, 0, 0, -1, 1, 0, 0, 0, -1, 0, again 0, 0, 0, 0. So this completes the first this problem. So next, one more problem. So this is one more model paper problem they're given. So write down 3 cross 3 matrix for the following triangle graph. The first row has the -1 in the column and they've given what vectors x1, x2, x3 are in its null space. How do you know 1, 0, 0 is not in the row space? We have to find that. So say as usual, we'll first find the incidence matrix. So incidence matrix, if we find what we get, 1, -1, 0, -1, 0, 1, 0, -1, 1. Then what vectors are in its null space? Here they're not given the equation. They're directly told to find the null space. Null space means what you have to find? Same thing. Ax is equal to 0. So what is A? 1, -1, 0, -1, 0, 1, 0, -1, 1 into x. What is X? X we can here 3 nodes are there. So X will be X1, X2, X3 transpose. So X1, X2, X3 equal to 0. Next, if we find the equations, we'll get X1 minus X2 is equal to 0. X3 minus X1 is equal to 0. Then again, X3 minus X2 equal to 0. So if we solve this, we'll get X1 is equal to X2 is equal to X3. So finally, the null space will be, null space n will be equal to some a or constant into 1, 1, 1. So it's because the null space is always spanned by the vector 1. So this is finding the null space. Now they find, how do you know that 1, 0, 0 is not in the row, is not in its row space? We have to find whether it is in the row space or it is not. So for that we have to prove that this given vector R and the null space, they are perpendicular. If we prove that it is perpendicular, then it exists. If it is not perpendicular, then it will not exist in the row space. So for that, first we'll take this matrix. We will take the general form of the null matrix A, null space. Then the given R is, we will take the transpose of that. R is 1, 0, 0. This is the given. This is n. N into R is equal to 0. So n into R equal to 0 we have to prove. So what is n here? So n into R. So A will get n into R is what we'll get. N into R will get it as A, which is not equal to 0. Therefore, 1, 0, 0. So therefore, this is not perpendicular to the row space. So it does not null space. So it does not, this vector, this does not exist in the row space. So this is one type of problem they can ask. Last problem. So this is this only 3 types of problems they can ask. So with conductance, the conductance will be given. C1 is 1, C2, C3 is 2 they've given. Multiply matrices, you have to find A transpose CA and F also they have given the 1, 0, minus 1. We have to find the solution to the given equation. A transpose CAX is equal to F. We have to write the potentials X and the currents Y is equal to minus CX. What is this? This is nothing but the Ohm's law. We have to apply the Ohm's law of this triangle graph, and when the current source F, this is the current source they've given, it goes from the node 1 into node 1 and out from the node 3. It will go out from the node 3. So this problem we'll find. First, as usual, we have to first find the incidence matrix. Minus 1, 1, 0, minus 1, 0, 1, 0, minus 1, 1. Again, for this, we have to find A transpose because we have to find A transpose C into A. So A transpose is minus 1, 0, 1, 0, minus 1, 0, 1, 1. Now the conductance they have given 1, C2, C3 as 2. So this conductance, how we have to find the conductance matrix? So for the first node, we have to write it in the diagonal, principal diagonal we have to write. Rest of the things we have to fill as 0. So C1 as 1 for the first node, rest 2 as 0. Next here it is 0. Principal diagonal value you have to write. It as 2, 0. Again 0, 0, 2. So fill that in the principal diagonal, rest all the values will be zeros. So this is how we form the conductance matrix. Now we have to find the A transpose CA. A transpose CA. So if we multiply this A transpose C into A, we'll get the matrix as, I think everybody know matrix multiplication. So I'll write the direct answer. 3 minus 1 minus 2 minus 1 3 minus 2 minus 2 minus 2 4. This is the first solution to the first part, that is to find A transpose CA. So now the current source is given. We have to find A transpose CA into X is equal to F. So A transpose CA into X is equal to F. So this is A transpose CA. So that is 3 minus 1 minus 2 minus 1 3 minus 2 minus 2 minus 2 4. Now into X. Since there are 3 nodes, we'll assume X as X1, X2, X3 transpose. So we'll write it as X1, X2, X3, which is equal to F. F is also given there in the question. So it is 1, 0, minus 1. F is also given. After writing this, for this we'll form the A is to F augmented matrix. Three minus 1 minus 1 minus 2 minus 1 3 minus 2 minus 2 minus 2 4. So 1 0 minus 1. So we'll apply the transformations and solve. And I'll rub this part. Minus 1 minus 2 minus 1 3 minus 2 minus 2 minus 2 4 1 0 minus 1. So we'll apply the transformations now. So first we'll reverse the rows. R2 as R1. So I'll get it as 1 minus 1 3 minus 2 0. Again we'll get it as 3 minus 1 minus 2 1. Then minus 2 4 is to minus 1. Then again we'll apply the transformation. We'll first reduce it to the echelon form. R2 plus 3 R1. Then one more will apply R to 3 plus minus 2 into R1. Then we'll get it as minus 1 3 minus 2 0 8 minus 8 is to 0. Again 0 minus 8 8 is to minus 1. Now again we'll apply the transformation to find 1 by 8 of R2 one more is 1 by 8 of R3. Two transformation will apply. Then we'll get it as minus 1 3 minus 2 is to 0 0 1 minus 1 is to 1 by 8. Again 0 minus 1 1 is to minus 1 by 8. Again we'll apply one transformation here. R3 plus R2. So if I apply this, last row will become equal to 0. So -1, 3, -2 is to 0. 0, 1, -1 is to 1 by 8. Again we'll get 0, 0, 0 is to 0. So it has been reduced to echelon form. Then we can form the equations. So it is minus x1 plus 3x2 minus 3x3 is equal to 0. One more equation is x2 minus x3 is equal to 1 by 8. Now here also we'll assume one values. Some values we'll assume. Let x2 be 1. So if we substitute x2 as 1 and we solve the equation, we will get the values as x3 as 7 by 8. We can solve, you can solve these equations by your own. Substitute assume x2 as 1, any value you can assume, and just find the values. X3 as 7 by 8 will get x1 as 5 by 4, again x2 as 1. So these are the 4 potential values.
Yeah, this also vary, Pramod.
Yes, ma'am, this also varies.
Because here having they knows in the first module, they have two equations with 3 unknowns. Then what type of solutions we are expecting? Infinitely many solutions. Either maybe assume either maybe in terms
So
of x1 or at x plus any one of the form. Therefore, we get infinitely many. You are choosing, therefore, each person we can't expecting same solution. Correct, Pramod?
yes, ma'am. So you can
Okay.
assume any of
Okay.
the values,
Thank you.
any one value, and find rest of the values. That's it. So we'll get the.
Why? Because they have. Yeah, correct. You have 2 equations with 3 unknowns. Therefore, we are expecting infinitely many. Okay.
Yes. Now this is the this part of the function. So find the solution to A transpose CAX is equal to F. So for this part of the solution, we have found out this. So these are the potentials to the nodes. So x1 as how much? 5 by 4, x2 as 1, and x3 as 7 by 8. Now let us find the currents. Currents in these edges. What is the flow of current in these edges? For that we apply Ohm's law. So Ohm's law, they've also already given in the question, minus C AX. Sometimes they will not give in the question. You should remember the equation. So the Ohm's law is equal to Y. What is minus conductance matrix? We formed the equation. So it is negative of that matrix. That's it. Directly will multiply in the. So it is -1, 0, 0. Principal diagonal values you have tried the conductance. So other two are 2 and 2. So you'll get 0, -2, 0, 0, 0, -2. Again, x value. So x we have already assumed x value. Ax, what is A? -1, 1, 0. This is the this is not the matrix. -1, 0, 1. A is nothing but the incidence matrix. 0, -1, 1. X values, we have already found the X values in the previous one. What are the X1 values? It is 5 by 4, 1, and 7 by 8. So 3 values we found out already. So if we multiply all these 3, then we'll get the solution as for the Y as 1 by 4, 3 by 4, and 1 by 4. So these are the currents. So finally, if we multiply these 3 matrix, we'll get the current values, and we have also found out the potential values. So finally, again you have to redraw the graph, redraw the given graph. So and you have to write the solution. That's all. So here x1 value what we have got 5 by 4. X2 value what you have got 1. X3 value what we have got 7 by 8. And the current values what we have got here y1 as edge 1 is y1, that is 1 by 4. Y2 what we have got 3 by 4. And this what we have got y3 as 1 by 4. So this is the final solution. So this will end this complete problem. So only these three types of problems can be asked from the graphs and networks part of the applications. So this ends this part. Ma'am?
Yeah, I'm there. Yeah, anybody have a question what they explained, Pramod, Kavya and Meghana? If you have any question based on graphs and networks, you're free to ask the question. Hello?
Hello. In the first question, while they asked, we have to find two solutions for A transpose y is equal to 0. For first solution, we substituted some values and found out. Was there any reason to find the second solution? We just didn't multiply the first solution by a constant and called it the second solution.
So we have to assume two values for the each time to find the new unique solutions.
Okay, but like if we multiply the entire thing by a constant, it will be unique, right? Is there any reason why we say like we resubstitute and find the new solution again?
It is not like everybody will get the same solution. Usually we solve the problem like by assuming that we don't multiply there.
Yes, in that equation, you please show it to promote that equation. They're having a number of unknowns is more than number of equations, right? Hello, Pramod? Yeah, Jayant? I'm audible? Jayant?
Yes, ma'am. Yes, ma'am.
Yeah, you already saw that equation. How many equations?
You are muted, ma'am.
Yeah, Jayant, are you remember how many equations are there? Actually, number of unknowns more than number of equations, right, Jayant?
Yes, ma'am. Yes, ma'am.
Yeah. What you know, what type of solution have in the system of equations, right? Unique
Yes, ma'am.
solution, infinity, maybe is the inconsistent means they don't have a solution. Here, what happened? They had what I observed 5 unknowns. They have only three equations. At that time, they had to assume no, two values. Instead
Yes.
of taking K1, K2, Pramod is taken 1, 1. That's all.
Okay. Yes,
Without
ma'am.
knowing two unknowns, that the what? Yes, Pramod.
The solutions will not be unique. Any values you can assume, ma'am. Any two pairs.
Yeah, his question is why, Jayant, please repeat your question.
Ma'am, like let's say we got our answer as 1 minus 1, 1, and we can multiply at 2 and say the another second solution is 2 minus 2, 2. That is also a
Yeah,
different solution.
choice of your choice. I am understood what you are asking the question. Your choice. What we told, we get infinite number of solution because we have to assume at a time two values. Then only is possible to proceed other three values. Correct?
Yes, ma'am.
Yeah. What he told, we get infinitely number of solution. I quoted that also. we can't expecting same set of solution from the other. Yeah,
Yes, ma'am.
that's also possible. Jayant.
Okay, ma'am.
Okay. Are you clear? Are you get a solution for this your question?
Yes, ma'am. Yes, ma'am.
Yes. Okay.
And Jayant, if for your question, if you take out the constant out, that still reduces to the same vector again. So there's no point of multiplying it with a constant for all the vectors, I guess. So
Yeah,
like if
yeah.
you
Yeah.
Again, we'll
2
get same.
minus 2 and 2, just take 2 common, you still remain with 1 minus 1 and 1. So cross multiply 2 to the other side, you still have the same solution.
Okay.
Yeah. You are expecting different type of solutions. Okay. Okay, ma. What you given clarification is correct.
Okay. Got it.
Yeah.
Jayant is clear?
Yes, ma'am. Yes, ma'am. It's clear.
Yeah.
Any other participants have a question?
Jayant, which branch you are?
Computer science, ma'am. Fourth sem.
Okay. Okay. Very good. Okay. Anybody have a question for this? Madam is asking, Gunavati madam. Please unmute and ask.
For the model papers, they've asked one question from this graphs and networks.
Yeah, Pramod, you please share your material along with the solution of the problem, okay? Pramod?
Ma'am, I'll share.
Hello? Yeah.
Hello.
I'll share
Yes,
tomorrow. Yeah. You please share it what you explain all three along with the problem with solution. That's useful for those who are attending today class. Anybody have a question? Yeah, Gunavati?
Yes, ma'am.
You please wind up and then say thanks for all three. Yes.
Yes, ma'am. Thank you for all the participants. Actually, a good job from the team of the presenters. Thank you very much. Thank you all. I will end the session. Tomorrow's session will start at 7 p.m. So we'll share the link in the WhatsApp group. Yes, ma'am. We'll end, ma'am.
Yeah, one minute, Gunavati. I sorry, Pramod, Kavya, and Meghana for busy schedule. I forgotten to share whatever today link. That's why they joined late. Because of me, they joined late. Sorry once again. And thank you very much for Meghana, Pramod, and Kavya. You are once asked you last week itself within few days with your busy schedule you are accept our invitation and then you have to given a very nice presentation and then I hope everyone even though they are not attend sir madam is going to share the recording link in the YouTube. Madam is going to share Dr. Gunavati madam is going to share that YouTube link maybe in tomorrow. Yeah. Her busy schedule for Gunavati, she did recording everything. Again, I'm going to thanks to Gunavati ma'am because you know that NAC and NBA preparation is going on. In spite of busy schedule, she's agreed to join that and then she take care all the things. Thank you once again, all the participants, Dr. Gunavati ma'am, and all those who are our faculty members are joined this webinar to support this webinar. Thank you once again. And once again, lastly, I thank all three resource persons. They given very wonderful, good presentation. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Uh,
Thank you for
Thank
the
you, ma'am.
opportunity. Thank you.
Yeah. Thank you.
ma'am.
Uh,
We'll end
bye.
the session,
See you.
ma'am. Yes, ma'am.
Yeah. Bye. See you and take care in the. We are seeing the tomorrow. Okay. Bye.